So today's lecture is on constitutional isomers. Constitutional isomers are molecules of the same formula but have different connectivity. So that means the sigma bonding framework will be different within each distinct constitutional isomer. Isomers of the same formula will have the same number of pi bonds and or rings in their structures. So for example, if you draw a molecule that correctly has no pi bonds or rings in its structure that matches the formula, any constitutional isomer drawn from it will not have a pi bond or be composed of any kind of ring in its structure either. So what we saw in the quiz one of the most straightforward isomers was simply this straight chain primary alcohol. There was not a pi bond in that structure, nor did it contain a ring, and none of the correct constitutional isomers did either. However, say we had a different molecule that we were drawing constitutional isomers of, perhaps an alkene. Well, an alkene has a pi bond. And so in this 5-carbon alkene, any constitutional isomer that we draw must have either one pi bond or one ring. So, for example, this would be a constitutional isomer of that alkene. But also this would be, because the whole molecule is composed of a ring. And you can fill in the hydrogens and count. The formula for all of these should come out to be C5H10. And you can draw some more if you wish, but that's not the point of today. What I want to do is do another example. This will be an amine functional group. And what we want to do is draw all the possible constitutional isomers. The formula we are given is C4H11N. I would suggest go ahead and try to draw at least a few, or try and draw them all, and then check to see my systematic approach to doing it, which you very well may adopt in the future. Anytime you draw constitutional isomers, usually you start by putting all of the carbons in a line, and then whatever else is there, just tacking that on the end. And that is a logical starting point. It gives you a nice big chunk with the carbon atoms that you will rearrange later to make isomers. Once you do this, you can also, if it's the first molecule that you're drawing, check to make sure the hydrogens, when you fill them in to give everything an octet, actually add up to the number that they must to satisfy the formula. And so we should all know by now that if nitrogen is going to be neutral and in its most stable form, it will have 3 bonds and a lone pair. And carbon will have 4 bonds. And so we'll fill in the hydrogens to satisfy those requirements. And so when we go about doing that, and we count everything up, we can see that we have, indeed, 11 hydrogens. Now, this brings an interesting point. Some people have made mistakes in the past. In their first attempt to draw a constitutional isomer, they may simply change the molecule's geometrical orientation, or its orientation in 3-dimensional space, but they haven't changed the connectivity. This sigma bonding backbone is the same. It's 4 carbons connected in a row, and then a nitrogen on the end. And so if you were to fill in the hydrogens, it might make it look different. But these are the same exact molecule because the connectivity is the same. If we were to describe what was bonded to what, we would have the same exact description for either of these molecules. It doesn't matter that the nitrogen is hanging downward. All that matters here is that this nitrogen is bonded to that carbon. And in this structure, this nitrogen is bonded to that carbon as well. The other carbons are all the same, in the same orientation anyway. So they're obviously the same. So this is not a constitutional isomer. It's the same molecule. Usually once you draw the Lewis structure, you should convert that to a skeletal structure and then only work with the skeletal structures. Then you don't have to keep track of the hydrogens. If we notice that we do not have a pi bond or a ring in the structure, we know we cannot include a pi bond or a ring in anything we draw. So we don't really have to worry about hydrogens anymore as long as we satisfy the octet rule in all of our drawings. And so we'll work from this structure. The logical thing to do, if we have a 4-carbon chain with a nitrogen on the end, is to then break that down into a chain that's 1 carbon shorter. And so, for example, if we start with a 3-carbon chain, well, we can put the nitrogen on the end of a 3-carbon chain. And then we have to think about possibilities for where that other carbon can go. And so the carbon, if we put it on the end, well, that'll just make the identical molecule over here. It'll be a 4-carbon chain with a nitrogen on the end. However, if we put the carbon branching off this point, it's certainly a different molecule. The connectivity is different. This carbon here is bonded to 1, 2, 3 carbons, whereas over here there weren't any carbons bonded to 3 other carbons. That alone makes them different. And you can go in and add where the hydrogens should be, and you'll count 11 hydrogens total in this structure. Applying the same approach, we can draw another 3-carbon chain with a nitrogen on the end. And so if we had an extra carbon on the end or an extra carbon on this carbon, now we can put an extra carbon here, for example. And now we have 3 different molecules. Notice all of these are primary amines. When you look at this structure, it's tempting to take the same backbone and then move the nitrogen group over one. If we look at these two structures, however, if we're just describing the connectivity, we can say that the nitrogen is bonded to a carbon that's the 2nd carbon from the end of the chain. Well, that could apply to either one of these. Well, we could say, well, it's also bonded, that carbon that it's bonded to is also the 3rd carbon from the other end of the chain. Well, that applies to both of these. So they're the same molecule. Many times it's hard to envision that unless you actually go about drawing out the structure. If we go again with a 3-carbon chain, and instead of putting the nitrogen on the end, because we've exhausted those possibilities, we put the nitrogen in the middle. Well, now we have some new possibilities. Again, if we add a carbon on the end, well, that'll just be a 4-carbon chain, and we've seen that result. But if we put the other carbon in the middle, well, now we have 3 carbons bonded to this carbon, which is also bonded to the nitrogen. And so we've got another distinct primary amine. All the nitrogens are only bonded to 1 carbon, so those are primary. That exhausts all the primary amines. Now, if you haven't done so already, take a stab at trying to make the secondary amines. And it will help, since you know you're going to focus only on secondary amines, to think about what that requirement is. Secondary amines must have a nitrogen with a lone pair bonded to 2 carbons and then bonded to 1 hydrogen. So try and incorporate that in your structures and see how many distinct possibilities you have. The way I would start off in a skeletal structure would look just like this. I have 2 more carbons to add. If I want to be fair, I can add 1 to each end. And this is certainly a new molecule, and it certainly satisfies the molecular formula. If I start off with the same scaffold and I want to show favoritism and be cruel, then I can add both carbons to only one end, and we have a different molecule. We've got 1, 2, 3 carbons here, the 4th carbon on that end, both secondary amines. So where do you go from here? Well, you can always start off with the same scaffold. If we use the option of only adding 1 carbon to each endpoint, well, then we're going to end up with the same one. But there's a different way to orient a 3-carbon chain than is shown here. And so, for example, if we bond the nitrogen to the middle of a 3-carbon chain, that will result in yet a different structure. And so these are the 3 secondary amines that are possible. Lastly, try to find tertiary amines. So for a tertiary amine, your scaffold's going to look like this. And that's eaten up almost all the atoms of note in our formula. And so if our scaffold initially looks like this, we can add a carbon just onto one end, and then we're done. And there's no other way to modify this, because no matter where you add that carbon, the nitrogen will be bonded to 1 2-carbon chain and 2 1-carbon chains. So for example, if we start our scaffold like this, and instead of putting the bond over here, I decide to make it down there, these are the same exact molecule. Again, the nitrogen is bonded to 2 1-carbon chains and 1 2-carbon chain. Same molecule. So that wraps it up. And these are our 8 constitutional isomers of amines. You can identify that functional group, and you can classify it primary, secondary, and tertiary. Use this same kind of approach, a systematic one, where after each molecule you check the structure for connectivity differences, and then you can apply this to any problem-solving technique with constitutional isomers, regardless of the functional group. Good luck.